Hello. So for this video, we will be talking about the formulation of DE. Okay, so formulation or rather formation of a DE. So for this topic, okay, so how do we usually form a DE? We usually do what we call the elimination of arbitrary constants. Okay, elimination of arbitrary constants. Now, what is an arbitrary constant? Remember when you do a or rather an integration process, for example, the integral of x dx, okay, which equates to x squared over 2, right, plus c. This c is an arbitrary constant. Okay, so this is a constant produced by the differentiation process. Now, if you do double derivative, you will have two arbitrary constants. Sorry, double integration. Okay, two arbitrary constants, triple integration, three arbitrary constants, and so on and so forth. Okay, so for us to create the differential equation, we need to eliminate these arbitrary constants. Okay, so in an equation, there are constants which are not produced by the integration process. Okay, those there are constants that are need not be eliminated. Okay, we are only eliminating the constants produced by the integration process, right? So we have some uh, methods in the elimination of these arbitrary constants, okay, and we will discuss them in separate videos. So for this video, we will be talking about the elimination, rather isolation method. Okay, so isolation method, or let's say the first method that we will discuss. Okay, so isolation. In this method, we will isolate the constant and then differentiate, because the uh, derivative of the constant or the derivative of a constant is equal to 0. Okay, so if we will isolate that constant, right, and then derive, it will be equal to 0. Alright, so let's have this example. X minus a squared plus y squared is equals to a squared. Okay, so naturally, the call this one, the constant here is a. So if we were to isolate a from the other parts of the equation, okay, and then derive both sides, a will now be equal to 0, and we have eliminated the constant successfully. Okay, so let's try. Let's simplify this one, because this will result to a squared. We have a squared on the other side of the equation. The a squareds will cancel out each other. So x parenthesis x minus a squared will be equal to, so this is a difference of two squares, rather this is FOIL method, apology. So x squared minus 2ax plus a squared plus y squared is equals to a squared, right? So a squared, this will cancel out. See, we will try to take the long process here. Okay, now we have a here. We can transfer this to the other side. Again, our goal is to isolate the constant. So what will be left on the left side will be x squared plus y squared, right? So a squared, transfer the other a squared here, minus a squared. Transfer 2ax to the other side, so plus 2ax. Then the 2a squareds will cancel out each other. Okay. So what will be left is x squared plus y squared is equals to 2ax. Again, the goal is to separate a, right? So separating A, we will have okay, so x squared plus y squared all over x is equals to 2a. I left 2 because 2 is also a constant. So to reduce whatever we have to solve as well. So if there are other constants that is attached to our target constant, we can leave it there. And when we derive both sides, right? So this side will now be equal to 0. So we will be left with the derivative of, okay, x squared plus y squared all over x is equals to 0. Okay. Now, for this case, which is a quotient rule, I find it easier to derive this one by selecting a dependent variable and selecting an independent variable. Okay, to make the differentiation process easier. So let's say I will choose x as the independent variable. Although not stated, but if the that is this is not the 100% of the case, right? But usually if there is a y and an x in an equation, y is usually the dependent variable and then x is the and then independent variable, just because of the they are the traditional notations for this one. Okay, so we have a quotient rule here. So quotient rule states that if we have u and v, the derivative of u and v, we will have v du minus u dv. Okay, we have v du minus u dv all over v squared, right? So in this case, v is x, our u is x squared plus y squared. Okay, so x times the derivative of x squared plus y squared in terms of x. Okay, all right. So x squared plus y squared. I'm taking the long process here so that you can see the totality of the process. The next is u. So u here is x squared plus y squared times dv. So the derivative of x in terms of x will be equal to 1 all over v squared. X squared is equal to 0. Now the only problem part or the most complicated part here is the derivative of x squared plus y squared in terms of x. Okay, as well as when we cross multiply x squared, or let's do, okay, we can eliminate x squared. If we cross multiply x squared to both sides, okay, so multiplying x squared to both sides, now x squared here will be cancelled, but on the other side it will be equal to 0. So we will be left here with x times the derivative of x squared plus y squared in terms of x. Now the derivative of x squared in terms of x, this will be 2x. Derivative of y squared in terms of x, that will be 2y. And then 1y will be dy over dx. Minus x squared plus y squared, okay, is equal to 0. Now if this looks complicated, we can replace dy over dx with y prime so that we can write the equation easier or lighter. Now we will have, okay, we will have this one. So x times 2x is 2x squared x times 2y is 2xy, then dy over dx, again, we will write this as y prime, minus x squared minus y squared is equals to 0. Okay, then let's see if we can simplify more terms. So we have 2x squared here, we have x squared here, so 2x squared minus x squared, then we can combine. So the what will be left is 2xy y prime plus x squared minus y squared is equal to 0. Now this will be, no, we can no longer simplify this one, so this will be our differential equation. Okay, so this will be the answer. Again, isolation method, isolate the uh, arbitrary constant to one side of the equation so that when you perform the derivative, okay, the constant will now be eliminated because the derivative of a constant is equal to 0. Then perform the derivative of the other side. Alright, so that's it for the first method or the isolation method. So let's go to the second method, which is substitution method. Okay. Okay, for the next method, we have the substitution method. In this case, we will not try to isolate the arbitrary constant, but instead, we will try to uh, find a substitute equivalent to that arbitrary constant, which does not contain the constant itself. Okay, I know the explanation is a bit a bit complicated, but let's show with the same example. Okay, so x minus a squared plus y squared is equals to a squared. Okay, so this one seems like a no-brainer because you can try to eliminate some of the terms first before you can proceed to the derivatives or the differentiation, or you can differentiate immediately and then try to eliminate some terms later. Okay, in this case, if we will try to do implicit differentiation on this one, okay, so in the substitution method, we are mostly using implicit differentiation. Okay, so this one will be a chain method, rather chain rule. Okay, so we have quantity x minus a, quantity squared. So by implicit differentiation, this will be 2 times x minus a. Okay, then the derivative of x minus a will be dx plus the derivative of y squared will be 2y y prime. Okay, is equals to 0. Alright, then what we will do here is this is sorry, this should not be y prime. 2y dy is equal to 0. Okay, now what happens here is we are left with a, or we are left with our uh, arbitrary constant. Okay, with no way of, what do you call this one, eliminating. I think I forgot to mention that the number of derivatives needed in formulating ADE is equivalent to the number of arbitrary constants. So if you have one arbitrary constant, the highest derivative, or rather the highest number of derivatives that you should perform is also 1. If you have two arbitrary constants, it should be 2, or rather it should be up to the second derivative. If it is if 3 arbitrary constants, then you should derive up to the third derivative. Okay, again, arbitrary constants is the result of the integration process. So 2 integration, double integration, 2 constants, 2 derivatives, etc., etc. In the example, x minus quantity x minus a squared plus y squared is equals to a squared, we only have one constant. So, we can only do one derivative. Okay. Now, we are left with a. So, we need to find a substitute for a. Okay, which does not contain a. Okay. Now, let's try to find a possible uh, substitute for a from our original equation. Now, the original equation is x minus a squared plus y squared is equals to a squared. Now, x minus a squared plus y squared is equals to a squared. If you remember our uh, process in the isolation method earlier, we expand this term. So, x squared minus 2ax plus a squared is equals to y squared. Apologies, plus y squared is equals to a squared. Okay, now if we will eliminate a squared, we will left with x squared plus y squared over 2x is equals to a. Okay, so this is the same earlier with our isolation method, except that we removed, or rather we have uh, we let 2 stay on the right side. But this time, since we are only concerned with a, okay, so we have transposed 2 as well. Now, this is an equivalent of a without a in this equation, okay? So, this does not contain a. X squared plus y squared over 2x, right? So, if we substitute this to our derived equation, we will have, by the way, if we can observe that in this part here, we have 2 on this term, we have 2 on this term. Okay, we can eliminate 2 by multiplying 1/2 to the whole equation. Okay, so we will have x minus a dx plus y dy is equal to 0. Okay, so substitute the value of a that we have solved. So x minus, right, x squared plus y squared all over 2x dx. Okay, plus y dy is equals to 0. Then simplify, right? So here we have x minus x squared plus y squared, okay, all over 2x. So we need to have a common denominator here, which will be 2x. Okay, so 2x, right? So 2x divided by 1, that will be 2x times x, so will be 2x squared. Okay, minus, so this will be x squared plus y squared. So we have successfully combined x minus x squared plus y squared all over 2x using their common, using a common denominator. So dx, then plus y dy is equal to 0. Okay, so for the next line, we can remove 2x. Okay, we can remove 2x here by multiplying 2x to both sides, right? So 2x, so 2x will be cancelled on this side. So what will be left is 2x squared minus x squared. So x squared minus y squared, right? Dx. Okay. Plus, so 2x times y, 2xy dy is equal to 0. Now, looking back at the answer from the isolation method, which is this 2xy prime plus x squared minus x squared is equals to 0, right? This looks quite different, right? But again, recall that when we divide the whole equation by dx, okay, we will have here the dx will be cancelled, so x squared minus y squared plus 2xy. Then we will have here dy over dx, and dy over dx is y prime is equal to 0. So now they look the same, right? So x squared plus y squared plus 2xy prime is equal to 0. Right? So that is our substitution method. Okay. And isolation method in the elimination of arbitrary constants. Alright, so for the notable differences, so for the isolation, you will mostly encounter the quotient rule. For the substitution method, you will have to use implicit differentiation. Right, so this ends our video for we have more methods for the elimination of arbitrary constants. For now, this ends the video for the isolation and substitution methods.